problem is about reactances, and it reads, at what frequency in hertz are the reactances of a 52 millihenry inductor and a 76 microfarad capacitor equal? So here we have an LCR circuit. Here's the inductor, here's the capacitor, here is the AC current with a certain frequency F, and there's a resistance R in there. We may use it or we don't have to. And from that then results the impedance, written as Z equals the square root of R squared plus the reactances XL minus XC, and those two are squared, and take the square root of that. All of these are in ohms. I think we can see that if this is ohms, well, then this has to be in ohms here as well, and then taking the square root of the square here will then means then also the impedance is in ohms. In order to get the smallest impedance and therefore the largest current, these two here would have to be a minimum. Respectively, these here would come out to be 0, the subtraction between the two, in order to yield the smallest impedance and largest current. And then that of course means what the problem says, XL equals XC. So XL minus XC equals 0, and of course XL equals XC. And now all I have to do is grab the reactances, the formula for those. So this one is going to be 1 over 2 pi the frequency times the capacitance, and the other one is given as 2 pi times the frequency times the inductance. Nothing divides out here because this is in the numerator on the left and this is in the denominator on the right hand side. They want to know what the frequency is, so I'm going to do the algebra on this one here. Get all of this first to the other side, and I have 4 pi squared F squared L times C, and then I get all of this stuff back down here and take the square root, and you may do the algebra yourself, but it's really straightforward that this is going to come out to 1 over 2 pi times the square root of L times C. And then it's just a matter of plugging in numbers. So the L here is given as, what was it again, 52 millihenry. So of course that is 0.052 Henry. And the capacitor is given as 76 microfarad. So 76 times 10 to the negative 6 farad. Plug those in, those are all standard units, and then the frequency will come out to hertz. And then if this circuit was part of, for example, an analog radio, then at this point it would resonate at that particular frequency due to the adjusted reactances. This circuit, this problem is about a circuit that includes an inductance and the resistor. So it reads, a circuit consists of a 250 ohm resistor and a 0.200 Henry inductor. These two elements are connected in series across a generator that has a frequency of 106 Hz and a voltage of 234 volts. What is the current in the circuit? Determine the phase angle between the current and the voltage of the generator. So in order to determine the current, we would have to determine what the impedance is and then divide the impedance into the voltage. So here we go. Since there is no capacitor, the capacitive reactance is 0. And then what we have here is Z equals R squared plus the inductive reactance squared. Take the square root, and of course here it's plugging in XL equals 2 pi times the frequency times the inductance, and those are all given. The frequency is given as 106 Hertz, and the inductance is given as 0.200 Henry. The resistance is given as 215 ohms, and then the RMS current, root mean squared, is computed as the voltage divided by that impedance that would be calculated. And since everything is going to be in standard units, it's going to come out to amps. And the voltage, of course, is also given as 234 volts. And then determine the phase angle between the current and the voltage of the generator is given as tangent phi equals XL minus XC over R, respectively. There is no XC, so it's XL over R. Oh, need a little bit more space because well, you'll see in a moment. XL over R, and because we need to figure out what the angle is, I take the inverse tangent on that side of these two. And that also means here, because if I need the XL here, we actually need a value over here for the reactance in ohms. Plug that in, take the inverse tangent, come up with, if your calculator's in degrees, come up with by how many degrees the current is lagging behind the voltage in the circuit. So this is a problem about an LCR circuit in which the inductance and the capacitance are in parallel. And it says, for the circuit shown in the drawing, find the current provided by the generator when the frequency is very large and when it is very small. Now, when I copied this circuit here, as you can see, that came straight from the problem. I don't recall why or how I cut off this wire here on the very left, so there it is. Alright. So, something apparently must happen when the current is very large and, when the frequency is very large or when it is very small, and that would depend on the reactances that are given. So XC, at least I'm trying to do that, XC equals 1 over 2 pi frequency times capacitance. So when the current, when the frequency is very large F, we can see that the reactance would be approaching 0, and in turn, for the inductive reactance, for a very large frequency, that inductive reactance would become very large. So basically then we would have a large impedance here, and we would have a very small impedance here. And now, as you recall from parallel circuits, we would have a larger current go through this part respectively. If we add these up here as reciprocals, we would come up, if this one here is very large compared to this one, basically a total impedance for the entire circuit that just describes this top part here, with this one here virtually no current going through here. So yep, the current is just going through the top part. And what we would have to look at is that the impedance is then basically going to be the resistor on the top, again because this one here is in parallel to the other one with a very large Z. It's the current only goes to the top one, and again, if you do that, 1 over Z plus 1 over Z equals 1 over the total Z, you come up with that the total Z is basically this one here respectively. Actually, let me write that down. Now that I said it twice, might as well write it down. So the top plus the bottom and that would be the total that says top here, and this one says total. So if this one here is very large, then I divide by it and I basically come up with that. As I divide by a large number, this is basically 0, that fraction, and the Z top is the Z total. So that's what I'm saying here. That's why I write it like this here. So this here would be at 290 ohms. And let's see, what are they actually asking for? Oh, the current. So at this point here, it's just a matter of saying, okay, in this case, the current is the given voltage of 75 ohms divided by 260. What did I just say? The current RMS equals 75 volts divided by the resistance on the top, which is 290 ohms. And that then comes out to some number in amps. 75 divided by 290 is going to be so roughly 0.3, a little bit less than 0.3 amps. Okay, then for the very small frequency, I'm going to try to copy all of this one here and put it further down. Okay, I was able to pretty much copy everything over here, up here. I guess I could have written that. That is the Z total. Alright, so now we have a very small frequency. Trying to write an A there. So that means that the capacitive reactance is going to be very large, and therefore the inductive reactance is basically going to go towards 0 compared to the resistance. And that means that here we have a large impedance on the top. I guess I could have written this one as well as top, and the other one is bottom. And here we are going to have a small one. Small impedance here. And then again, when I look at these here in parallel, that means here small and here large. So the top one is actually the one that the fraction is no longer there because I divide by a large number, so it's basically 0. And it's pretty much that the total impedance comes out to being the impedance at the bottom. So total here, and that equals then the resistance at the bottom. And again, the reason is that for a small impedance here, the current is going to flow through this part here and totally pretty much bypasses the top part. And then, yeah, the rest is that I forgot to erase one little thing here. This should be reading then the bottom here, and so it's basically going to be 75 volts divided by 710 ohms, which is in the neighborhood of 0.1 amps. This one here would be described as a low-pass filter, as this one here would allow low frequencies to pass through, while the other one here would be a high-pass filter because it allows high frequencies to go through, and it suppresses low frequency just like the other one down here suppresses high frequencies.